The same general rules are going to apply if the mirror is bent the other way. I've talked about concave mirrors up until this point. Now let's consider the case of a convex mirror. Keep in mind that if we have just an object that is emitting light, we can try to figure out where it is by drawing a line through the center point. That line is going to reflect backwards, and because it's totally normal to the surface. And then we can draw another line at some angle. It's going to angle in is going to be equal to angle out. We kind of see in straight lines. So we trace that back right over here, and we see the object or the image is going to be on the other side. One way to kind of remember, which ones are negative and which ones are not negative is over here there's going to be light. Over here there's going to be no light. So the things that are over here are going to be negative. So over here S prime is going to be negative, and also the radius of curvature is going to be negative. For true images, we'll consider kind of that lighted up arrow for a second. We're going to figure out where its image is going to be very much the same way. We draw a line, a ray through the center point. If it goes through the center point, it's going to hit normal to the surface and bounce right back at it. Then there's going to be one other ray that's going to bounce kind of like that, and it's going to trace ourselves back, and bam, you have the tip of your arrow. So where image is going to be right here, you can see that is going to be up, so it's not going to be a negative magnification. It's going to be smaller, so magnification will be less than 1. The same general rules are going to apply, and you can kind of see because S prime is going to be negative, the magnification will be positive, so the image will be upright. We also call these virtual images because it's on the opposite side of the light. The same general rules for focal point and focal length are going to apply for a convex mirror. If we consider parallel light coming in, so the image or the object is going to be at infinity, then we're going to reflect off this surface. Angle in is equal to angle out. Do that for all of these rays coming in, and where they trace together, kind of trace this guy in, trace this guy in, trace that guy in, trace that guy in, trace that guy in. That's still going to be the focal point. It's going to have some focal length, f, only now it's on the side where there is no light, so we call it a virtual focal point. You could also conceptually just kind of reverse your rays and have light coming in this way, that way, that way, and that way, and say that the image would be at infinity because you'd have parallel light coming out. For kind of a real-life application of this, consider Santa looking at himself in a light bulb. Obviously he's going to appear much smaller, so Santa might be 1.6 meters high. That's the object height. The image is going to be a virtual image. It's going to be inside of the light bulb, and it's going to be obviously much smaller, and Santa's still going to be standing up, so it's going to be upright. We know how far away Santa's standing from the surface. We've measured our light bulb, gotten the radius of curvature of that guy, and we therefore can say that the focal length is going to be the radius divided by 2, so now we have our focal length, and we apply the same equation. 1 over object height plus 1 over object distance, 1 over image distance is going to be equal to 1 divided by the focal length. What we're kind of interested in is how tall is Santa going to be. So we can say that the 1 over image distance is going to be equal to 1 divided by the focal length minus 1 over the object distance. So that's going to be 1 divided by 0.018 meters minus 1 divided by 0.75 meters. That's going to allow me to calculate my image distance. That's going to be equal to negative 0.0176 meters. That means it's going to be on the inside. That's what the negative means. We can then say that the magnification is going to be equal to negative object distance divided by image distance. So that's going to be, wait a second, scratch that. It's going to be negative image distance divided by object distance. So that's going to be negative 0.10176 divided by 0.75. The magnification is going to be quite small. It's going to be positive 0.002 2, 3, 4. Again, no units. And lastly, we say that the image distance is going to be equal to the magnification, or image height is going to be magnification multiplied by the object height, 0.0234 multiplied by 1.6, and I'm going to get a very small object, 0.038 meters. The benefit is he also looks skinnier. So now let's kind of put all this together and talk about some graphical methods for mirrors. So it's be fairly important for you to be able to do this to check to see if your image is where you think it is for your calculations. What we do is we say light's going to emanate from an object and it's going to go in all directions. We're going to pick a couple of principal rays that are very useful to us. So if we have our object right here, we're going to pick light that's going parallel to that object, and we know that the light's going parallel to the axis right here is going to must go through the focal point. So ray number 1 is going to bounce, come in this direction right there, and here we have kind of what we call the optical axis. It's kind of the base right here, and where that intersects, where line number 1 is going to intersect with the optical axis, that's going to be the focal point. I'm going to clear those guys. We can also then draw a ray through the focal point, and that's going to be ray 2 right here. So now ray 2 is going to go through the focal point. It's going to reflect. It's going to be parallel to the axis. So where those two lines meet, that tells me where my image is actually located at. Now it may be useful to draw a couple of more just for verification. We know that if we consider ray 3, a ray going through the center of curvature is going to reflect directly back on itself. And so it's going to go like that, then it's going to come right back to the very tippy top. So a third verification. And then if you just kind of draw a ray at the vertex, V right there, which is the optical axis, it's just going to be symmetrical, and you're going to get your image. This is also going to work for convex mirrors. Here we have ray 1 coming parallel to the surface. It's going to reflect like that. You kind of trace it back through the virtual focal point. And then maybe draw, let's just go with ray 3, the one that's normal to the surface. Going through the center of curvature, it's going to reflect back on itself. And it kind of goes in there. And here we have our virtual image. So let's take a quick look at example 34.4 and look at these rays for several different scenarios. So here if we have an object that's outside of the center of curvature, we draw our line that's parallel with it, must go through the focal point. And I generally draw lines 2 or 3, I almost never draw lines 4 myself. I draw a line through the center of curvature. It tells me that my image is going to be just right here. It's going to be smaller and it's going to be inverted. It's also going to be real because it's on the same side as the light. Now suppose I went ahead and I moved my my object to the exact center of curvature. I go ahead and I draw these lines, and it turns out that my image is going to be inverted and also at the center of curvature. It's also going to be real. You can kind of take a look at this equation right here and convince yourself that the object distance and image distance must be the same. Then I go ahead and I move my object to the focal point, and we know that light is going to essentially bounce and then go away kind of in parallel. So in this case you can take a look at this equation right here and convince yourself that because the focal length and the object distance are the same, the image distance must be equal to infinity, so we're not going to see an image. And lastly, once you move inside of the focal point, we still draw the same lines. We would still draw a line going in and then coming out in the parallel direction, going through the focal point. We would draw, say, maybe line 3 that's going to just kind of go back and forth like that. You could draw a line from the focal point going away in parallel, and where these objects all trace back is going to be the location of the image. In this case, the image is going to be on the side where there is no light, so it's going to be a virtual image, and it's also going to be larger than the object, and it's also going to be erect, meaning that it's going to be pointing in the same direction as the original object. Now, the reason I spent so much time talking about curved mirrors is because lenses are going to have a lot of very similar properties. Now, lenses is just going to essentially be a curved piece of glass or plastic. Let's talk about a converging lens for a second here. This is also going to be a convex lens. If we have light that is coming in parallel to the lens right here, it's going to essentially get focused down just like a magnifying glass, and it's going to go into what we call a focal point. And this focal length is going to kind of be the distance from the center. We're going to have kind of this optical axis, and it's going to pass through the center, kind of splitting this lens in two. And we're actually going to have two focal points. We're going to have a focal point on this side of the mirror, or one on this side of the mirror, lens, because you could conceivably pass light into this lens from either that direction or that direction. This focal length is always going to be positive for a converging lens, and it's going to be the same distance on each side of the lens. We could also say if we have light at a source that is located at the focal length, then we can kind of just reverse these rays, and we're going to get parallel rays coming out on the other side of the lens. Images for lenses are going to be formed the exact same manner as with curved mirrors. If we have this object right here, we're going to have some object distance s from the center of the mirror. We're going to have some focal length, and we're going to have some image distance, so calling that s prime. We find it in pretty much the same manner as we did. We have some parallel to the optical axis ray that's going to go through the lens and get bent down through the focal point, and keep on going like that. If we draw a line starting from the very tip of the arrow here, and it goes through the very center of the lens as well as through this optical axis right here, it's going to pass through the lens undeflected, much like the one that hit the very normal surface of the mirror. And the intersection of those two is going to be where the tip of this image is located. We have the object distance, object height y. We have the image height y prime. Keep in mind that both s and s prime are positive. S is because it's on the same side as the incoming light, and s prime because it's on the same side as the outgoing light. And the same equations are going to apply. 1 over s plus 1 over s prime is equal to 1 divided by the focal length. We can still define the magnification to be equal to the image height divided by the object height, which is also going to be negative object distance divided by image distance. So all of these equations are still going to apply. We can also have a diverging lens or a concave lens, and what this lens is going to do is it's going to bend light away from it. You can kind of imagine light coming in to a diverging lens like this. It's going to spread it out, and it's still going to have some focal lengths, and if you were to trace all of these rays kind of back right over here, they're going to go to the focal length. Keep in mind that for diverging lenses, f is going to be negative, so this lens would have a focal length of, say, negative 10 centimeters. And it's going to have two focal points. It's going to have one on this point and one on this side, because light can go either way through this lens. You could also kind of go the opposite way and say we could have light coming in from all these weird funky angles, and the light that comes out is going to be parallel. Just kind of trace all these guys inwards, and they all point directly towards the focal length.